Okay, section 5.4 is not going to take as long as section 5.3 did. So kind of some things to think about that we've learned about this year is if you have an original function and you take the derivative of it, you get like a function about like something moving. You take the derivative of it and you get the velocity. If you take derivative of velocity, you get acceleration. Well, now we're just going to work backwards. So if you want to find velocity but you have acceleration, you'd integrate acceleration to find velocity, or you'd integrate velocity to find position. So let's look at this example. This is on page 401 in your book, so you can look at that as well. But they said VT is volume, but this is the change in volume. Okay, we know the change in volume right here, but we're trying to figure out the volume, how much gas was used in the first 2 hours of this motor boat. So we know VT, or V prime T, and we're just trying to find VT. So we need to integrate this. So in terms of T, so it'd be 5T minus, now we're gonna want this to be a T to the fourth, right? But think when you take the derivative of T to the fourth, you get 4T to the third, and we just want it to be T to the third. So that would become 1/4 right here. So again, you can always check your work by taking the integral or derivative. 5T becomes 5, and then this would become minus 1 T to the third, and that's what we want. Okay, so now it wants to know how much gas is used in the first 2 hours. Well, that's just assuming you started at 0 hours and you went up to 2 hours. So we want to evaluate this from 0 to the 2. So using the fundamental theorem of calculus, we would just need to take the V at time 2 minus the V at 0. So if we plug a 2 into this function, we get 5 times 2, which is 10, minus a fourth of 2 to the fourth. So 2 to the fourth is 16, and a fourth of 16 is 4, minus, and then if we plug a 0 in, obviously it's 0 minus 0. So our answer would be 6, but let's make sure we're answering the question. How much gas is used? That would be 6 gallons. So there we go. Pretty simple. That one's not too bad. If you flip the page over or go to the next page, honestly, it would be page 23. And here we're talking about a particle moving along a straight line. They give us the velocity is the s prime of t, and that's t squared minus t minus 6. They want us to find the displacement of the particle. So what we're going to do, see how this is s prime? We want to find, they're using s as the displacement, the letter s. So I'm just going to say s of t equals displacement. So let's take the integral of s prime of t. So t squared, we know that'd be a t to the third, right? But we don't want a 3 out front. We want to be blank, or a 1, so we do 1/3. Okay? Minus t, so we do t squared, but again, we want just to be minus 1t, so we need to multiply this by 1/2, because 2 times a half would turn in just to minus t, and then we would have a minus 6t. And we want to evaluate this from 1 to 4. So again, you can kind of show that work right here. We want to evaluate this from 1 to 4. So we want to find s without the prime on it of 4 minus s of 1. So you just plug 4 in here and plug 1 in here, and I'll save you guys a little bit of time. It ends up being a negative number, negative 4.5. Now what does that mean? So we're talking about displacement of a particle, and how can a displacement be negative? It's moving along a straight line, so if it's moving to the right, it's positive. So since it's a negative 4.5, that means 4.5 meters. Is this in meters? Oh yeah, meters per second. Meters to the left. To find the total distance traveled, this is definitely a little bit more work. To find the total distance traveled, we are going to look back at velocity. Remember, velocity, if the velocity is negative, the particle is still moving a distance. So what you want to do is to find your total distance traveled is you have to find the absolute value of velocity. So anytime this velocity is equal to 0 or negative, you want to take the absolute value of that. So our velocity function is given at the top. So we first need to determine when this is positive and when this is negative. You should recognize this is a parabola, a U-shaped parabola, and it's going to dip down below the x-axis some. You can type it into Desmos to get these answers, but it's really easy to factor. It'd be t minus 3 and t plus 2. So the places on the graph where the x-intercepts are going to be at positive 3 and at negative 2. Okay, and I know negative 2 is not part of what we need, but the graph's going to kind of look like this. And we want to go from 1 to 4. So at 1 to 4, where is it a negative velocity and where is it a positive velocity? I shouldn't have colored in the shaded region. It's kind of like this part's a negative velocity and this part's a positive velocity. So the velocity is positive in our range. We only care from 1 to 4 at 3 to 4. And our velocity is negative from, we only care about 1 to 4, right? From 1 to 3. Okay, so you have to kind of do these separately. You have to integrate the velocity just from 3 to 4 by itself and make it positive if it's not, and just from 1 to 3, and again, make it positive if it's not. So we are going to integrate the velocity from 1 to 3 and from 3 to 4. Okay, I just wanted to kind of go in order. So what you do here, and this is in the book, is we want to do the opposite of the like the negative velocity, because a negative times a negative is a positive. And here we want to integrate the actual velocity. So we're going to use what we had above, this formula right here. We're going to use that, but it's just, we have to do this opposite. We have to make it negative from 1 to 3. And again, this is explained in the book if you don't like my explanation. But so the negative velocity function would be negative 1/3 t to the third plus 1/2 t squared plus 6t. And we're going to evaluate that only from 1 to 3. And then we're going to add to that the integration of the velocity from 3 to 4, leaving it exactly what it is, using it as a positive 1/3 minus 1/2 minus 6t, and we're going to evaluate that from 3 to 4. So again, you would plug the 3 in, plug the 1 in, and you'd subtract those answers. Okay, plug the 4 in, plug the 3 in, and then, oops, no, we're adding, that's right. Subtract those answers. Okay, so you can do the math, but you should get 61 over 6, which is roughly 10.17 meters. Total distance traveled. So this is a distance and this is a distance. It's kind of like this is that first part of the distance and this is the second part of the distance. Distance has to be positive. Position or displacement can be negative, means to the left. You guys know velocity means you can have a negative velocity, like if something's on its way down, or if it's down below the x-axis. So hopefully that makes somewhat of sense. That's kind of a tricky one. And now indefinite integrals is going to feel easy compared to this. This is where you want to kind of look in your book on page 398, and we are going to notice all these examples on this page, and this is our last page. All these examples, they don't have any numbers to plug in. Okay, they just want us to do, that's why it's indefinite. It doesn't have a definite answer, it's indefinite, but you basically are still just going to find the antiderivative. So for example 1, if this is our function right here and we want to take the antiderivative of that, 10x to the 4th, hopefully that makes sense, that'd become an x to the 5th, and we want it to become a 10 right here. So when you take the derivative, that would become 5x to the 4th, so we'd want to multiply that by 2, because 5 times 2 would be 10x to the 4th, okay? And then minus 2 secant squared, if you guys look in the book, they have showed the derivative of secant squared is equal to tan x plus c. But since it's minus, you would do minus 2 tan x because of the minus and the 2, and then just plus c. And that, you can just put an equal sign. That is what this equals, like just in the general form. Okay? All right, this one's a little bit more tricky. Cosine over sine squared. So before I actually take the derivative of this, let's kind of just change the term. Let's kind of just change how we're writing this. So what we could do is we could leave cosine over sine, we like that, and multiply it by what? So we would need another sign on the bottom. So 1 over sine. Okay, and can you guys think of what 1 over sine is equal to? That's equal to cosecant. So again, I've not integrated anything. I'm still just rewriting this in a different form. Okay, we know cosine over sine is cotangent times 1 over sine is cosecant. And now if you look on page 398, you're going to see this on page 398. I'm looking too. So it's on the right column, the third one from the bottom. Oh, I should have a d theta at the end of all these. Apologize. Okay, you can look. This is one of them in the chart. It's not like you just magically know this. It's one of them in the chart, and it would be, now I'm equal to, so don't use the integral anymore. This is equal to negative cosecant of theta, and then the plus c. Okay? Because it could be like anything in a function family. And that's explained in the third video that I had you watch. That wasn't my video. All right, and finally, this one we can go straight to integration. So equals, we want this to be an x to the fourth, but we want to turn in just to x to the third. So what fraction would I need right here? So I multiply 4 by it and I get 1. 1/4. Minus, okay, I want this to be an x squared, but I want it to be minus 6x. So if this 2 multiplies by 3, 2 times 3 would be negative 6x. And then we just have to remember to write the plus c at the end of these. And that's it. Good luck with your quiz. Hopefully everything you need to know, you now know.